This is research that I've done with my friends, Rodolfo Benda and Tabata Gomez. The work was inspired, motivated, if you will, by Frankie. Oh, never mind, I guess I was motivated by the theory of direct learning, which is an approach, an elaboration of direct perception that has been peddled by my friends David Jacobs and myself in recent years. Direct perception would hold that perception or action is a function of some information, and that information is specific to the environment. There are other processes that we worry about in more detail than is traditional, namely the process of calibration, in which one changes the function that perception is of information, but not the information. And learning, which is a change in the variable upon which perception or action is based. But our idea of information departs somewhat from the traditional ecological view, namely that we consider the information to be just one locus in an information space. So we would replace the single information variable by a space, and then to say that you occupy a locus in the space, and then learning becomes a process by which you traverse the space from a place that perhaps is not so valuable, not so useful, to a place that is more useful. We take all three of these processes, perception, calibration, and learning, to be information-guided processes, and would expect that the information that guides these processes are in fact different. Information for perception are the sorts of things we talk about all the time, like optical acceleration, whereas information for calibration might be some longer-term variable, like error, and the information for learning would be an even longer-term variable, such as a covariation between error and some other variable. And finally, a process that we worry about is a change of intention. Namely, when you change your intention from, say, catching a fly ball to escaping a lob grenade, you will, in effect, likely enter a different information space, or reaching to something versus locomoting to another space. These ideas have been applied in the last few years to dynamic touch, walking, and some of our calibration work, perception of kinetic properties, pole balancing, most recently in JDP. And today I'd like to talk about some research that tries to apply these ideas to bimanual coordination, and in particular to a bimanual tapping task. Much richer than the single tapping task that was talked about earlier. Subjects are seated at a computer with their fingers on two keys, and they are told simply, tap in an alternating way in such a way that the cursor goes inside the circle. To achieve that, they would have to really center it, they would have to tap every 500 milliseconds with their right hand, and then at a 90-degree phase lag from that with their left hand. Okay, so we ran 20 participants on 30 trials with 50 tapping cycles, so basically 1,500 tapping pairs. And they received feedback, obviously, from the cursor, namely the horizontal position of the cursor was based on their period error, okay, the inter-right interval, if you will, and the vertical position of the cursor was based on, or milliseconds, their error in the left-right interval. Okay, so that's the task. And we're providing information about what the correct period is and what the correct phase is, but bear in mind that what we as experimenters decide the information is may or may not be what the information is that they use, that they attend to. A good departure point from trying to understand the learning or the calibration in this task is going from kind of an intrinsic dynamics of tapping to these informed dynamics as specified by the position of the cursor. So to sort of describe that, let's consider, for example, the Hocking-Kelso-Bunce model, which is going to probably be the best representation of the underlying or intrinsic dynamics. Now, I've depicted it here in two ways, with some arbitrary parameterizations. The standard contour plot on the left and a density plot on the right. And I'll use the density plot because it's going to be the way I'll present data. So the period is on the bottom from a very short period, 200 milliseconds up to 1,000 milliseconds. So 500 in the middle is where you want to be, and vertically. Here you see the in-phase attractor is the real dark one, and the anti-phase attractor is the lighter top one, but of course they're supposed to be somewhere in the middle. And we'll use that sort of to compare the data. I'll present the data just in terms of scatter plots of where each pair occurred. That is, what was the interval between the right paired with right to left interval. And so there's an example of a subject who is kind of stuck at in an anti-phase attractor. Okay? So that describes, if you will, the starting point, the ending point. What are the goals like? Well, we might imagine that there's a goal at 500, at a period of 500, a goal representing the phase of 90 degrees out of phase, and we can, multiply those together to have a final characterization of the goal of where they want their responses to be. So we want to think of these as attractors that you're going from those attractors on the top to the attractors on the bottom. And we can also express these attractors in terms of vector fields. There's a corresponding vector field for there's a phase attractor. Yeah, for the frequency attractor, phase attractor, and both. Okay. Now, to figure out the difficulty of learning, we might first ask what happens when we combine that last goal attractor with the Hocking-Kelso-Bunce model. And what you're going to see here very clearly in a messy picture is that it's going to be much easier to calibrate your frequency than to calibrate your phase. Okay? One more time. See, you can move in these directions very easily, but now if you try to go from, let's say, in phase to, or anti-phase to the required phase, or the desired phase, then you're going against the gradient. So, one prediction, just looking at these, is it's going to be easier to learn frequency than phase. Okay, of the 20 participants, 2 of them didn't learn squat. Of the 20 participants, 8 behaved in this way. That is to say, they demonstrated a recalibration of their frequency, but persisted in tapping in antiphase. That is, according to intrinsic dynamics. So here's a picture of that. What do we have here? This is one subject. All 1,500 of his trials, or hers, divided up into ninths. So this is what they were at the beginning, first, second, third, all the way down to the end. What do we see here? We see a broad frequency tuning to start with. Right? The frequencies are sort of spread across from about, or the period from about 300 up to 1,000. Over the course of learning, that narrows. right? They do start to respond to a much narrower range of frequency. Importantly, the frequency they start responding to is not 500. That period, it is instead less than 500. Whoops, come back. And that is going to tell us that the information by which they recalibrate is not the information that was hypothesized in that field. Okay. In fact, what they were doing, and just take my word for this, is that they were modulating their period as a function of not the distance to the center, but the actual distance to the target. Let me very quickly show how that works. This is a vector field representing the covariation of radial distance and the interval. All right? Now, when we had the other one, it zeroed you right in on 500, right? When it was just the lateral distance. But now, the radial distance, if we zoom in on a particular part, what we will notice is that in fact, using this information to guide your selection of period, in fact, puts you in a faster regimen. Okay? So we're seeing here the use of different information than we expected. Okay, let me move on to some other subjects. 5 subjects appeared to learn the test. And let me just leave it there, right? And some of them were very good right from the get-go. And they ended up where they should be in this little region. Another subject who started out with a little more variability and then zoomed in to be in the correct target region. 4 participants, however, were most interesting because it appears that they, in fact, adopted a different intention. Okay? And that intention seemed to be controlling the interval. And what I'm hypothesizing here, or arguing, is that they escape that HKD, anti-phase attractor, by doing something different. And the something different that they do is to try to recreate this pattern. Da-da, 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 da-da. Now, there are a couple ways you can do that. You can do it the right way. Left, right, no, right, right, left, right, left. You can do it left, right, you can go right, left, etc. So the job, should you have this change of intention, now becomes to find some new goals. Get the right interval, 125 milliseconds. Get it in the right order, right, left. And get the period also correct down to 500. Now, what would your distributions look like if you were to adopt this strategy? They would look like this. This would be the shape of a 125 millisecond attractor. That's ignorant of frequency, ignorant of hand order. Right? It would look like this. So what a subject might have to do then is make sure you get the right order. Yeah? And let me just stop at this point to try to give you some intuition about this funny shape. And that is, let's say you're doing it absolutely correct. Every 500 milliseconds and then 125. Yeah? If you now are going faster here, but still 125, what was a phase relationship of pi over 2, 90 degrees, would become a phase relationship of pi. Okay? So same interval, right, based on a longer period will give you different phases. So that's kind of the origin of this funny curve. Okay, and then of course your next task, in order to satisfy task demand, would be to narrow down the frequency. Okay, so narrow down the frequency. Notice importantly that this is an oriented circle. Right? That's going to come back to haunt us. Right? There's a correlation, if you will, again, that we were able to see up there. All right, so here's one of the subjects that did this very clear. Notice one thing about it is how rich and different the phase relationships are. You usually think, oh, you're locked into 90 degrees, or you're locked into, not 90, you're locked into 0, or you're locked into 180. But here we're seeing phase relationships all over the map, arguably because of this redefinition of the task. And here's another subject, did the same thing, but really didn't have so much the double, but just you really see this curvature down. Now, coming back to haunt us is the question of, did those other subjects that looked like they were really doing it, were in fact they controlling phase? And if we go back and look closely at some of those things, we see that they too were showing this relationship. So if you go back and analyze, now, and I didn't just, these aren't just eyeballing, right? I'm sort of describing these in a pretty loosey-goosey way. But I had some very, fancy fitting procedures for determining exactly what the attractor was that was used. I'm not going to talk about it like you. Pretty pictures, so we've got numbers, Mary, Lauren, numbers and pretty pictures. And in fact, all of the subjects who appeared to show the task demonstrated, at least in many of their nights, this relationship, this correlation, if you will, between phase and frequency. All right, let's slow down now. My time's up, and let me summarize. Our approach suggests that learning, change, in getting better at tasks can involve several kinds of processes, and in fact, we have seen several here. We saw recalibration to a particular variable. That was in the form of modulating frequency as a function of frequency error. We saw education of attention, learning, to use a different variable, and that came to us in the form of subjects saying, I'm going to start using this radial distance to modify my action, even though that variable did not really specify how to move in the space. And finally, we saw a change in intention, apparently a change in intention. Let me control intervals rather than tasks, and thereby escape difficult attractors. So difficult phase relationships can be executed if they are performed in perceptual tasks, which is a story, of course, that we have been hearing for a number of years now. Usually it's the experimenter, Mixner or Kovacs or whoever, that changes the task to turn a difficult phase relationship task into an easier perceptual task. And I might argue that that's exactly what the subjects themselves were doing here. Let's change a difficult motor task into an easier perceptual task. And that was sort of how the learning proceeded. And finally, we might note, and this is I think a theme that we've heard a couple times this afternoon, is that conclusions about variable use, calibration, and intention can be lost by averaging subjects' data. You really need, as Raoul suggested, to look at what's happening with individuals and be prepared, in fact, to see how they are changing over the course of the next go. Thank you for your attention.
We are short of time, but we still have questions. Depends on the length of the question and the response. So many?
Time for a post.
I would like to make a question, but I have no answer. This is my question. Like, I think in sports, for instance, there are so many variables that is tested, and that players are constantly learning or doing it. And how could I narrow or how could I change in sports tasks? I would actually hear your thoughts on it.
Well, it's definitely nothing that we started with a simple task. I mean, well, actually, our pole balancing thing was, you know, fairly complex and challenging, and we tried to close it. But I think in the control of a sports activity, you know, multiple information sources are presumably involved, multiple aspects of action, and one might at least start getting the foot in the door by thinking about two tasks, you know, doing two tasks at once. And I think my, you know, friend and collaborator, David Jakob, is in fact doing some of that work now. Let's now bring together multiple tasks and see how we can understand their working together. But at some level, to get this system to work, you know, you really sort of need to understand, in harking back to the kinds of things that Michael Kirby suggested, you know, 20 years ago, you really need to know what the needs of the action system are to ask what perception might do for you. And of course then what information the action system might create that helps guide itself. Many questions, there's a lot of work that needs to be done. You know, science is hard, and then you die. And answering, you know, applications to sports, I think is one of those ones that's very hard.
So we have another question.
If intention can be lost by averaging participants' data and individual information so relevant, how could you make compatible the scientific requirement of objectivity in data?
First off, I think what we often do is control intention in an experiment. You know, and mostly all the subjects adopt the same intention. You know, you instruct people to this. And I think kind of like one cool thing about this experiment was in fact that there were some degrees of freedom. Just, here's a task, we're not going to tell you what to do, just get that thing in the circle, and then they just did what they did. And we saw this little track where it seems some people did this, you know, could adopt this intention and that intention. So I think it's absolutely, you know, intention is absolutely available to us as a thing to be studied, quite objectively. It's not some spooky, you know, internal thing. Intentions can be manipulated, and sometimes, you know, I think in this case, they can be figured out a posteriori. So it doesn't scare me, you know. But then again.
Okay, thank you. Nice talking to you.